Statements. A statement is a sentence which can be judged to be either true or false. For instance, here we have 4 statements. Statement number 1 is 2 divides 4. Statement number 2, there are 5 days in a week. Statement number 3, x plus 1 is a factor of x squared minus 3x plus 1. And statement number 4 is A union B equals B union A. Now, of these 4 statements, not all of them are correct. Some of them are true and some of them are false. So if we look at the first statement, 2 divides 4, we know this is a true statement. Then if we go to number 2, there are 5 days in a week. Of course, it's a false statement because there are 7 days. Then we go to statement number 3, which states that x plus 1 is a factor of x squared minus 3x plus 1. Is it true that x plus 1 is a factor of x squared minus 3x plus 1? No, that's a false statement. Actually, it should be x minus 1. Now, in statement number 4, we know that the union between two sets A and B, that's commutative in nature. So that means A union B is going to be equals to B union A. So that means of the 4 statements, statement number 1 and statement number 4, these are 2 correct statements or true statements, whereas 2 and 3 are false statements. But nonetheless, all of them are statements. Even 2 and 3 are going to be considered as a statement because a statement has to be either true or false. However, if we give some command like bring me the cup of tea, now that's a command. A command cannot be a statement. Or if we ask someone a question, even a question like what is your name, that is not going to be treated as a statement. Okay. Now we also have mathematical statements. Now mathematical statements are also statements. That means it can be also judged to be either true or false. However, with an inclusion of the fact that it has to contain a mathematical relationship or mathematical relations. For instance, 1, that is a mathematical statement. We know 2 divides 4, that's a true statement. Number 3, statement number 3, although it is wrong, but it's a mathematical statement. X plus 1 is a factor of x squared minus 3x plus 1. It's a false mathematical statement. Then number 4, A union B equals B union A. So that is a true mathematical statement. However, if we look at statement number 2, there are 5 days in a week. This is not going to be considered as a mathematical statement. It is only a simple statement. Now, we will need to represent a given statement. We can represent a statement as Pn. So this is a notation that we'll be using to represent a statement. Some cases we can also use as P1n if we have multiple statements. So it will become P1n, P2n. So this is how we can represent a statement. For instance, if we consider the statement 2 divides 4, we can simply consider it to be Pn. Right. Then we can consider the next statement to be P1n. There are 5 days in a week. The third statement is P2n such that x plus 1 is a factor of x squared minus 3x plus 1. And the fourth one is P3n such that A union B equals B union A. So here we have a statement 10 times n plus 3 is prime. We need to check the validity of the statement. So here what we'll do, we'll first consider the statement to be denoted by the notation Pn. Let Pn be such that this is a statement such that 10n plus 3 is prime. Fine. Now what we'll do, now here n represents a natural number. So for the first natural number, when we choose n to be equals to 1, then we have P of n equals to 1. Then what we'll do, we'll substitute this n with 1 to get 10 times 1 added to 3. So we're saying that 10 times 1 plus 3, which is actually equals to 13. We're saying that 13 is prime. Now is this a true statement? Yes. Definitely, this is a true mathematical statement. So we'll say that the statement Pn such that 10n plus 3 is prime is a true statement for n equals to 1. We'll also have to check for the other natural number. So if we choose n to be equals to 2, then this time we're going to get 10 times 2, that's 20. 20 added to 3, so that's going to be 23. So 23 is prime. Is this a true statement? Yes, this is a true mathematical statement and holds true for n equals to 2. However, if we now choose n equals to 3, then we have 10 times 3, that's 30. 30 added to 3, that's going to be 33. Now 33 is not prime. Now since 33 is not prime, so that means our statement 10n plus 3 is prime is an invalid statement for n equals to 3. Since it's not getting satisfied for one value of n, which is n equals to 3, so we are going to stop here and we'll say that the definition here, we can say that P of n such that 10n plus 3 is prime is an incorrect statement. That means that this is not a true statement. So that's how we check the validity of a given statement. So here we are given a statement Pn, and the statement is that n cube plus n is divisible by 3. Now we have to check whether if the statement P of 3 is true, and also if it is true for P of 4. Okay, let us begin. So we have a statement P of n, which is given by n cube plus n is divisible by 3. Okay, now we will check if this is true for n equals to 3 or not. If we check for n equals to 3, all we have to do is substitute n with 3. So we get 3 cube added to 3. So 3 cube added to 3, that's equals to 30. Now is 30 divisible by 3? Definitely. 30 is indeed divisible by 3. So which leads us to believe that the statement P of 3 is true. So we have checked for the validity and it's a true mathematical statement. Next, what we'll do, we'll check for n equals to 4. So for P4, we're going to get 4 cube added to 4. This is going to be equals to, now 4 cube, that's 64. 64 added to 4, that's 68. Now is 68 divisible by 4? No, 68 is not divisible by 3. 68 is not divisible by 3, and this simply means that the statement P of 4 is untrue, or it's not true. It's not going to be valid if we choose n value to be equals to 4. It's only true for n equals to 3. Now in this example, we are given a statement Pn where we have 2 raised to the power of 3n minus 1 is divisible by 7. We have to obtain the statement P of n plus 1. So let's first write down the given statement. So here we have P of n, which is defined as 2 raised to the power of 3n minus 1 is divisible by 7. Fine. Now what we'll do, we're going to replace this n with n plus 1. So when we replace n with n plus 1, so our statement becomes P of n plus 1. Now all we have to do is replace 2 raised to the power of 3 times n, that n with n plus 1 minus 1, and the rest everything remains the same as divisible by 7. So this is how we rewrite the statement, original statement Pn as P of n plus 1. So here we have a statement P of n given by n square greater than 100. We need to show that P of r plus 1 is true whenever P of r is also true. Okay, let's try to understand this problem. So here we have a statement P of n such that n square is greater than 100. So this is a true statement. This is already given to us. So what we'll do, we'll first assume that P of r is also true. So let P of r is true. Now P of r being true, this simply means that we'll take the statement, the original statement, replace n with r, such that we get P of r square greater than 100. Now what we will do, we're going to add 2r plus 1 to both sides. So we have r squared, and we're going to add 2r plus 1 to both sides of the inequality. So here we have 100, and to it we are going to add 2r plus 1. The reason why we have done this, because now we know what is r squared plus 2r plus 1. This is simply the expansion of r plus 1 whole squared. So here we are saying that r plus 1 whole squared, that's greater than 100 added to 2r plus 1. Now let's try to think about this inequality. So here we have r plus 1 whole square, that's greater than 100 plus 2 of the terms, which is 2r plus 1. Now whatever be the value of r, then this statement can be also rewritten as r plus 1 whole square, that's also going to be greater than 100. So it's already greater than 100 plus 2r plus 1. So it's also going to be greater than 100. Now here we have to be a little bit careful with the condition that r being a natural number. This is only going to be true for natural number, and we know in the theory of mathematical induction we only deal with natural numbers. So any natural, if we consider the smallest natural number, which is 1, so we have 100 plus 2 times 1, so that's 1, so that's going to give us 103. So we're saying that r plus 100 and r plus 1 whole square, that's greater than 103, and since 103 is greater than 100, so we can say that r plus 1 whole square is going to be 100. In other words, what we have done here, we have considered the fact that 100 plus 2r plus 1, it's always greater than 100. Fine. Now, r plus 1 whole square greater than 3, this simply means that all we have done is stated the statement that p of r plus 1 such that r plus 1 whole squared, that's greater than 100. And this verifies that p of r plus 1, the statement is true, provided p of r is already true. Now, in this particular problem, it's given here that we have a statement Pn given by 3 raised to the power of n is greater than n. We need to show that p of n plus 1 is a true statement whenever p of n is also true. Okay, let us begin. So we'll start with the given mathematical statement given that p of n such that 3 raised to the power of n is greater than n. Now, in order to show that the following statement is also true for Pn minus 1, all we have to do is replace the n with n plus 1 such that we have p of n plus 1 such that 3 raised to the power of n plus 1 becomes greater than n plus 1. This is what we need to show. So how do we do that? So what we'll do, we'll start with the given statement 3 raised to the power of n greater than n, and we're going to multiply throughout with 3, so that we have 3 times 3 raised to the power of n greater than 3 times n. Now 3 multiplied to 3 raised to the power of n, this simply becomes 3 raised to the power of n plus 1 greater than 3 times n. However, we can rewrite 3n as n added to 2n. Now here we know that n is a natural number. Now what is the smallest natural number that's possible? The smallest natural number that's possible, that's equals to 1. So if we choose n equals to 1, then what happens to 2n? 2n is simply going to be equals to 2. So can we not say, since 2n equals to 2, we can say that 2n is such that it is always greater than 1. Which means that we can replace this with 1 and still the statement is going to stay valid. So we have 3 raised to the power of n plus 1 greater than n plus 1. In other words, what we have verified is that this simply means that the statement p of n plus 1 is also true. Fine. So this is how, with the help of mathematical induction, we can show that if a statement p of n is true, then p of n plus 1 must be also true for all natural numbers n. So here we have a statement p of n 2 raised to the power of 3n minus 1 is an integral multiple of 7. We need to show that the statement is true for p of r plus 1 whenever p of r is true. Okay, let us begin. So we'll start with the given statement. So here we are given a statement that is p of n such that 2 raised to the power of 3n minus 1. This expression is an integral multiple of 7. Now what we'll do, we'll suppose that let p of r be true as well. Now letting p of r be true as well simply means that we're going to replace n with r. So p of r is going to be such that we have the statement 2 raised to the power of 3 times r minus 1 is going to be an integral multiple. So this is a integral multiple of 7. Now, in order to show that the statement holds also true for p of r plus 1, all we have to do is, if we replace p of r with r plus 1 in this statement, then we need to have 2 raised to the power of 3 times r plus 1 minus 1. So this expression must be also an integral multiple of 7. Now, since it's already a true statement that 2 raised to the power of 3r minus 1 is an integral multiple of 7, so here we can suppose that 2 raised to the power of 3r minus 1 equals to an integral multiple of 7 means we'll make it equals to 7 times some natural number k. So where k is some natural number. Now what we'll do, we're going to rearrange this. So we have 2 raised to the power of 3r. This is going to be equals to, we're transposing the negative 1 to the right hand side, and adding with 7k to get 2 raised to the power of 3r equals to 1 plus 7k. Next, what we'll do, we're going to multiply both sides with 2 raised to the power of 3. So multiplying with 2 raised to the power of 3 on both sides gets 2 cubed multiplied to 2 raised to the power of 3r. This is going to be equals to 2 cubed multiplied to 1 plus 7k. Fine. Now, further simplification is going to give us 2 raised to the power of 3r added to 3. That is going to be equals to, so 2 cubed, that's 8. So we have 8 added to, so 7 times 8, that's 56. So we have 56k. Next, we have 2 raised to the power of 3 times r plus 1. Now what we'll do, we're going to subtract 1 from both sides. So that's going to give us negative 1 on the left hand side, and on the right hand side 8 minus 1, that's going to give us 7. So we have 7 added to 56k. Fine. So we now have 2 raised to the power of 3 times r plus 1 minus 1 equals to, now we can factor out 7 from both of the two terms on the right hand side. So that will be simply 7 multiplied to 1 added to 8k. Now we have already considered that k is some natural number, so which means that 8 times k is also going to be a natural number. Adding 1 to the natural number gives us a natural number. So what we have is a 7 multiplied to some natural number, which means that in short we can replace, so on the left hand side we have everything as it is. So we have 7 multiplied to, so this is going to be some other constant p, where p equals to 1 plus 8k is some natural number. Now what we have shown here, we have successfully shown here that the 2 raised to the power of 3 r plus 1 minus 1 is an integral. It is an integral multiple of 7, because here we have 7 times p on the right hand side. Now since it's an integral multiple of 7, so we have finally showed that the statement p of r plus 1 is true. So that means this is a true statement provided p of r is already true. So this brings us to the end of the lecture. So this was all about what a statement is. A statement is simply a sentence which can be judged to be either true or false. And we have mathematical statements. These are statements which contains mathematical relations.